In this lesson, we're going to look at Dalton's atomic theory as well as looking at some of the other experiments that were used to understand the structure of the atom. And we're not going to go into a lot of detail on these, but just kind of give you a bigger picture and a timeline of how this all occurred. If we look at a timeline starting back in the early 1800s when Dalton's atomic theory was proposed, we can look through time up until about 1932 when the last part of our modern atomic theory was discovered. So Dalton's atomic theory in 1800, we'll go through some of the tenets of that and talk about the ones that were accurate and the ones that not quite so much here in just a minute. But it's pretty close to what we know now about atoms. And so it's pretty impressive what they figured out in 1800 and the experiments they did with the technology that they had, or maybe say the lack of technology that they had. So in 1874, we were able to figure out that electrons existed. In 1898, radioactivity was discovered. 1897, they figured out the charge to mass ratio of the electron. And then following that up with 1909, the oil drop experiment let them figure out the charge of an electron. 1909 was a big year. We figured out the charge of an electron, as well as figuring out that an atom had a nucleus. But it wasn't until about 1932 that we figured out that there were neutrons that accounted for part of the mass of an atom. Let's look at some of the details of Dalton's atomic theory, which again was back in the early 1800s. What he proposed was that each element is composed of tiny, indestructible particles called atoms. Now we know this is false, that those particles, those atoms, can actually be broken down into protons, neutrons, and electrons, so they're not completely indestructible, but understanding that those atoms were discrete things was a big deal. All atoms of a given element have the same mass and other properties that distinguish them from other elements. So this is a kind of a half-half. So all atoms of a given element have the same mass. And what we'll find is that all atoms of the same element have the same number of protons, but can have a different number of neutrons, and therefore will have a different mass. So really close values, but not exact. The second part of this tenet is true, that have properties that distinguish them from other elements. So if we look at any one particular element, there's some set of properties that matches that element. And if we look at a different element, we're going to see a different set of properties. There may be some things in common, but that set of properties is unique to that element. Atoms combine in simple whole number ratios to form compounds. And this is true. So when we look at something like H2O, CO2, CH4, we see small whole number ratios of those atoms. Atoms of one element cannot change into atoms of another element in a chemical reaction. Atoms only change the way they are bound together with atoms. And this one is true. Note that we did clarify that we're talking about a chemical reaction, and we see rearrangements and different bondings and breaking bonds and making bonds, but all the atoms that are there at the beginning of a reaction are there at the end. They've changed form, they may change phase, but they're still there. But overall, the ideas that Dalton proposed were revolutionary at the time, and while it wasn't perfect, it was a great foundation for what followed in the discovery of the structure of an atom. One of the original models for an atom was that it was all kind of a positive charge pudding, and then there was negative charges scattered throughout. So they did an experiment by putting alpha rays through a sheet of very thin gold foil. And if we had seen the model that was predicted with this kind of plum pudding model where the positive charge was all over, the negative charge were scattered about, we would have seen that the alpha rays went straight through that sample, that foil sheet. However, what they found out was that most rays went straight through. Some rays were refracted or bent as they went through, and some were reflected as they went through. And what this told them was that they had this very small positively charged region within each atom. And that's what we've come to know as the nucleus. So with all the other information and experiments that were done, we came forward with the nuclear theory of the atom. And that is, the nucleus contains most of the mass and all of the positive charge of the atom. So within the nucleus are the protons and neutrons. And we'll talk more about these, but protons are positively charged and neutrons are neutral. So they have no charge. And this is all in this very dense nucleus in the middle of the atom. Most of the atom is actually empty space, and the electrons are dispersed throughout that. So if we want to imagine what an atom looks like, we can think about the nucleus in the middle, and that has our protons and neutrons. So it overall has a positive charge because we have positive and neutral species in there, and electrons, which are moving around in the atom outside of the nucleus. We simplified this model to show them in these nice orbits, and that's great to an extent. There are some limitations to this model. It's not a perfect model, but it's a great place to start because it helps us kind of imagine what's going on in that atom, where things are located. Other discoveries that led to the nuclear theory of atom, the modern atomic theory that we know today, is that the charge of the proton, I'll say plus one, is equal and opposite to the charge of an electron. And we label that as a minus one. We also discovered that electrically neutral atoms, so a species with no charge on it overall, must have the same number of protons and electrons, so the same number of positive and negative charges. The neutron was a little different because we could understand the positive and negative charges, but why would we even suspect that there were neutrons in an atom? Well, looking at hydrogen and helium, when they looked at hydrogen, they knew it had one proton and helium had two protons. However, when they looked at the mass of helium and the mass of hydrogen, although they were expecting a 2-to-1 ratio for the mass of helium to the mass of hydrogen, what they actually saw was a ratio of 4-to-1 helium to hydrogen's mass. And that's when they proposed the idea of neutrons to explain the difference in mass, but they didn't contribute to the positive or negative charge. They were a neutral species. So the discovery of the neutron was Chadwick's experiment, and this was in the 1930s, and kind of caps off where we ended up with atomic theory. Now we've gone on to learn other things in more detail. This is the basis for our modern atomic theory today. This is just a summary of the different experiments that helped us get to where we are today. And the first one is the cathode ray tube, which helped us figure out that there were, in fact, electrons, and also the charge to mass ratio of the electron. So we didn't know the charge, but we knew the charge to mass ratio. The names on these are not important. That's just who one of the scientists was working on these projects. The more important thing is to understand what these experiments told us. The next came the oil drop experiment, where we figured out the charge on the electron, and as a result, that also let us figure out the mass of an electron. Rutherford's gold foil experiment, which we discussed earlier, helped us identify that this atom has a nucleus, this positively charged, dense center of the atom. And then Chadwick's work let us figure out that we have neutrons.